Here's something that shouldn't be possible. Apple's newest, most advanced chip, the one riding on manufacturing physics the rest of the industry hasn't even touched yet, is not Apple's most powerful chip. Let that sink in. The M6 is built on a process so radically new, so fundamentally different from everything before it, that most fabs on the planet literally cannot produce it. Smaller transistors, better efficiency, next-generation architecture. And yet it's not sitting inside Apple's flagship desktop. No, the M6 has actually landed right inside the newly refreshed Mac Mini, while the Mac Studio is running an entirely different animal. Four M5 dies welded together into one absurd unified brain. So, which one actually wins? The chip built on tomorrow's physics, or the chip built by brute forcing four processors into thinking is one? Turns out it depends entirely on what you're asking it to do. And that contradiction is the entire story of this launch. Let's break down exactly what Apple built here because both of these chips are right, just right for completely different reasons. Apple pulled back the curtain on the M6 system-on-chip, built on TSMC's N2 process as the first commercial 2nm silicon. Powered by a 12-core CPU, featuring 2 super cores for performance cores and 6 efficiency cores, along with a 12-core GPU and a dual 16-core neural engine. The M6 brings unprecedented per-core speed straight to the compact Mac Mini. Simultaneously, Apple launched the Mac Studio built around the massive M5 Ultra, a quad-die package connecting 2 dual-die M5 Max chips via next-generation UltraFusion interconnects. The M6 establishes the next node generation for thin and light powerhouses. The Mac Studio pushes the mature M5 family to its absolute maximum thermal and memory envelope, targeting desktop professionals who need sustained throughput rather than per-watt efficiency. TSMC's published N2 targets anchor what we expect from the M6. The node shifts from FinFET to gate-all-around nanosheet transistors, a fundamental change improving electrostatic control and slashing leakage current. TSMC states N2 delivers up to 15% higher performance at the same power, or up to 30% lower power at the same performance, with logic density around 1.15 times that of N3E, with 170 gigabytes per second of unified memory bandwidth. Those node-level gains let the M6 sustain blazing clock speeds while dedicating more die area to GPU neural accelerators. That 2nm efficiency advantage makes the Mac Mini an absolute pint-sized powerhouse. Now the M5 Ultra inside the new Mac Studio. This is the more immediately contentious piece. Interconnecting 4 compute dies over a silicon interposer with over 4.4 terabytes per second of inter-die UltraFusion bandwidth, the M5 Ultra stacks up to a 36-core CPU, composed of 12 supercores and 24 performance cores, and an 80-core GPU. Apple states this quad-die topology presents a single unified memory pool with 1.2 terabytes per second of memory bandwidth to macOS, eliminating explicit data copies between CPU and GPU tasks. The practical effect? Large language model inference, 8K video editing, multi-stream ProRes workflows, all operating on model weights or frame buffers that exceed the capacity of discrete GPU cards in competing workstations. The quad-die configuration fundamentally changes thermal behavior. The Mac Studio's larger chassis and dual-fan thermal module let the M5 Ultra sustain higher power draw than any previous Apple Silicon part. Board shots reveal a more complex power delivery subsystem with additional phases around the interposer, suggesting the M5 Ultra draws significantly more under heavy multi-core load. 4 active dies generate more heat than 1, and the memory controllers stay active even when CPU or GPU sits idle. Benchmark debates have already split the community wide open. While previous generation M3 Ultra flagship setups pushed high-end multi-core limits, the M5 Ultra scales multi-core throughput and GPU compute dramatically higher, backed by up to 512 gigabytes of high-bandwidth unified memory. Critics point out that the M5 Ultra's multi-die topology carries inherent latency penalties in lightly threaded tasks, meaning the M6 new supercores outperform it in single-core responsiveness despite a much smaller overall footprint. This is the core spec war. The M6 wins per core efficiency and node leadership. The M5 Ultra wins raw multi-core throughput and colossal memory capacity. AI compute, is where both announcements converge. The M5 Ultra packs GPU neural accelerators across all 80 cores, enabling on-device inference for models with hundreds of billions of parameters without spilling to swap. The M6 brings that same class of AI acceleration to a lower power tier, driving local processing, real-time camera features, and agentic desktop workflows. Apple's public materials frame these two chips as complementary rather than competitive. The M6 is the efficiency play for everyday performance. The M5 Ultra is the capacity play for heavy desktop AI workstations. The desktop performance debate will rage until independent reviews measure sustained thermal throttling, memory compression overhead, and ProRes encode times under long-duration load. What's already crystal clear? The M6 establishes the 2-nanometer era and signals Apple's intent to keep the Mac on the leading edge of process technology. The M5 Ultra tests how far Apple can push a monolithic software abstraction over 4 physical dies. Together, they pressure x86 workstation vendors to justify higher power draw and discrete memory pools, and they raise the billion-dollar question. Will Apple eventually merge these paths, using the 2 nanometers node for a future M6 Ultra with an even larger die count? If this breakdown hit the mark for you, smash that like button, subscribe to Tech Market Pulse, and turn on notifications so you don't miss our next Silicon Deep Dive. Thanks for watching, and I'll see you in the next one.